Hey there again, 6A. Now we'll be looking on our final calculation in this series of calculations on radioactivity. Now the previous question looked on the sketch here of activity against time, and we sketched a nice best fit smooth curve showing the two half-lives for the sodium sample. Now this is just a follow-up question to the sketch that we previously plotted. Just want you to pay attention to the initial activity here as given in the previous in the first part of the question as 5.5 times 10 to the 5 becquerels, and our half-life of the sodium sample was 2.6 years. So now they're asking us to calculate the decay constant in per second, or disintegrations per second, of the sodium 22 sample. Right, again, we must first recall the equation that relates the half-life to the decay constant. Is this over T half, where the half-life must be in seconds. Now, they're given here the relation between 1 year and the number of seconds, as 1 year being equal to 3.15 times 10 to the 7 seconds. Right, so our decay constant lambda is going to be equal to ln2, the natural log of 2, which is just 0.693 over the value for t half in seconds. Now 1 year is 3.15 times 10 to the 7 seconds. Therefore, after one half-life, 2.6 years, the time in seconds will just be 2.6 times this big number right here to give us 8.1 times 10 to the 7 seconds. So just substituting that value here for a half-life in seconds times 10 to the 7 seconds, we get lambda being equal to 8.5 times 10 to the minus 9 per second. So that's our lambda, or decay constant. Now part 2 asks us to work out the number of atoms of sodium 22 in the sample initially. Again, if you remember the relation between activity and the number of atoms present as this, in terms of initial activity and the initial number of atoms, now we just represent it by putting a little subscript 0, and we get that. Now this is what they want us to find, N naught. Again, previously they've told us that the initial activity of the sample is 5.5 times 10 to the 5 becquerel, and we just worked out our lambda, or decay constant, to be 8.5 times 10 to the minus 9 per second. So again, by just transposing, we get N naught being equal to A naught over lambda, and we get 5.5 times 10 to the 5 all over lambda, which is 8.5 times 10 to the minus 9 per second. Plug this into your calculator and you should get 6.5 N naught being equal to 6.5 times 10 to the 13 atoms. Now, in the final part of the question, it asks us to calculate the time taken in seconds for the activity of the sample to fall from 1.0 times 10 to the 5 becquerel, so that's our initial activity in this case, to 0.75 times 10 to the 5 becquerel. That's our final activity. Right, now again, the equation that shows the radioactive decay of a sample in terms of its activity is A being equal to A naught e to the minus lambda t, and we're solving for this little t here in seconds. So let's first divide both sides of the equation by a naught. So you see that and that being cancelled. So we have a over a naught being equal to e to the minus lambda t. Taking natural logs of both sides, we have ln a over a naught being equal to minus lambda t. Now we have ln, our value for a is 0.75 times 10 to the 5 divided by a naught, which is 1.0 times 10 to the 5. And all of this is equal to minus lambda, which we calculated to be 8.5 times 10 to the minus 9 times this little t here, which we're trying to find. Now, plugging this into your calculator, you should get minus 0.29 being equal to this value here, all times t. Dividing, minus signs cancel, dividing through by 8.5 times 10 to the minus 9, 8.5 times 10 to the minus 9, that cancels that, therefore we get t being equal to 3.4 times 10 to the 7 seconds. Another way you could have done this is just looking on this relation again here. Since a is equal to lambda times n, we could have solved for n at this activity of 0.75 times 10 to the 5 becquerels, and you'd get this. A naught is equal to lambda times n naught, where a naught, or initial activity, is given as this. You can solve for n naught, and we should get this value right here. Just a little relation that I would like you to see is that since a is equal to a naught e to the minus lambda t and a is equal to lambda n, if you substitute for a, lambda n, and substitute thing for a naught, lambda n naught, lambdas here would cancel, giving us n equal n naught e to the minus lambda t. Again, those values that you found for n and n naught, applying natural logs here, and going through the process similarly, you should get t being equal to the same time in seconds, 3.4 times 10 to the 7 seconds. So there you have it. That's your series of calculations on radioactivity. See you in class where we'll have a radioactivity quiz. Later.